Hello everyone, my name is Dr. Subhasis Das. I am working as an associate professor in the Department of Electronics and Communication Engineering, SR University, Warangal, Telangana, India. This is my YouTube channel where I am going to regularly post some videos related to electronics engineering. Please do like, share and subscribe my YouTube channel. Today we are going to discuss one of the important topics in analog electronics or in electron devices and circuits. The topic of discussion is the full wave rectifier. In our earlier lectures, we have already discussed about the half wave rectifier and where we already learned about the rectification or basically what is the purpose of rectification or the definition of rectification. All these things we have learned, and we have also learned about some of the basic parameters to qualitatively or quantitatively discuss the different uh, merits and demerits of half wave rectifier. Today we shall discuss about the full wave rectifier, and later part of this video we will see that how we can overcome the disadvantages of half wave rectifier in this design of full wave rectifier. Okay, so first we will see what is full wave rectifier and kind of definitions and all these things. So it converts an AC voltage into a pulsating DC voltage using both half cycles of the applied AC voltage. So here comes the difference. If you remember the earlier video, we discussed that for the half wave rectifier, the only one half of the AC was converting to DC, other half was not converting. But here both the positive and negative cycles were converted to DC. And definitely while we are converting both the halves, we will be requiring two diodes instead of one diode. Okay. So one diode conducts during one half cycle while the other diode conducts during the other half cycle of the applied DC, and will make the circuit so designed that for the both the rectification, the final output voltage drop across a load resistor will be in the same direction and it will be DC in nature. Okay. So as we discussed earlier also, this one will also be pulsating DC, obviously, because here we are not using any filters. In later videos we will see that how we can make this more perfect DC by using the different types of filters. Okay, but for here this video we will discuss how we can design a full wave rectifier and how it can function for that. Okay, to design this full wave rectifier, there are basically two types of full wave rectifier we can design. First one is full wave rectifier with center tap transformer, and the other one is full wave rectifier without the transformer. That is, in other term, we are calling that type of rectifier as the bridge rectifier, right? So, for this video, we will concentrate our discussion only on the center tap transformer, right? Let's see how we can design that. Okay. So, here, as you can see, that this is a center tap transformer where this side is the primary coil and we have connected our line voltage to the primary side. right? And this portion, as you know, this is the transformer middle side, transformer core, and this side we have that secondary coil. And interestingly, if you notice that here is a center tap condition, right? And because of that thing, we are saying that this type of transformer is called the center tapped transformer. Okay, that means while the voltage is coming across this secondary coil, basically it is coming as half positive half this side and negative half this side. If it is 9 volt, so this side is 9 volt and this side is again 9 volt, so it will be total 18 volt. Okay, okay, forget about that thing. Let's now make our discussion in such a way that we will see the output as the AC converted into DC, right? So here we will see that the first diode. Okay, let's try to understand cycle wise. When the positive cycle comes, that means this side is getting positive and the center here, not the lower portion, here the center position will be the negative. Okay, and if you notice the circuit for this condition, we will see that this positive side and this is the P side of the diode, this is the N side of the diode. And again, if you see that inside, this one is going like this way and coming like this and going like this way. Okay, that means you can easily see that when this end becomes positive, the P side gets more positive than the N side. Okay, so that means this diode D1 will be in forward bias condition, right? So because of this, as we know, that diode D1 will act like a closed switch. That means it will conduct fully and there will be no such voltage drop. So that this load resistance will have a full voltage drop across this. Okay, that means in that case, if you notice here, we will see that we will see the output like this, right? So this is for the positive half cycle. Okay. Now, you might be thinking why I am saying that this circuit is going like this instead of going, it may go this side also. Okay, but that will not be the case because this side is not positive, so that means this diode is not conducting for the positive half cycle, right? So this path will not be followed for this condition, right? Now we will see that when it comes to the negative half cycle, right? So for the negative half cycle, look here at the bottom part of the transformer will get positive, and for this diode D2, this is P side and this is N side again, right? So what happens now? This side, this one is positive, which is connected to the P side of the diode, and again, if you follow the circuit, you will see that the circuit is going like this and coming like this and going to the center tap condition. Okay, and if you see this position is in lower potential than this position, that means your p type of the diode D2 is connected with the higher potential compared to the N side. That means your diode D2 is in forward bias condition, right? And when the forward bias condition is satisfied, this diode D2 will be conducting. Okay, and similarly the other path will not be followed this condition, so diode D1 will be turned off, so this path will be conducting and obviously there should be no voltage drop in this condition, right? And here this case also we will see the full voltage drop across this load resistance RL. Okay, so And for the output curve you will see the similar thing for the negative half cycle also. So what we found now, that for both the positive cycle and negative cycle we are getting the output in the similar fashion. So we can conclude here from this output nature that both the cycles are converted into DC. Okay, so now we understood the working principle of Fourier rectifier. Okay, the next slide will explain this thing in more detail. Okay, although we have already explained most of the things, but still I will just reiterate those things for your better understanding. Okay, so let Vi be the voltage to the primary of the transformer and given by the equation. Similarly, like the half wave also, we consider this condition first, the input voltage condition, and here Vm is the Vmax, which is the peak value of the sinusoidal wave. Okay, and here also the condition is Vm must be very greater than Vy, and Vy is the cut-in voltage of the diode. Let's say the cut-in voltage is 0.7 volt. That means your Vm must be very greater than Vy, right? So that is one condition applied. And when this is satisfied, then we will see that how the circuit is being followed and the output is given as the full wave rectification. Okay, so during the positive half cycle of the input signal, D1 becomes positive, and at the same time the anode of the D2 becomes negative, as I told earlier. That means D1 will conduct and D2 will not conduct. So the load current flows through D1, and with the voltage drop across RL will be equal to the input voltage, because when a diode conducts means there is no such voltage drop across it. So whatever the voltage, it will be fully uh, loaded at the load resistor, right? Okay, so this is for the positive half cycle. During the negative half cycle of the input signal, what happens? The opposite thing will happen now. The anode of D1 becomes negative and the anode of D2 becomes positive now. So the similar but the opposite. Okay. So D1 does not conduct this time and D2 conducts. So we will again see the similar kind of voltage drop across RL. But interestingly, we make our circuit such a way that for both the condition, the voltage drop are or the current flow direction are at the same direction for both the cycles. That means we will see the halves in the similar fashion or in the same side or same polarity. Okay, so the load current flows through D2 is the voltage drop across RL, which will be equal to the input voltage. So what you notice here that for the both the positive and the negative cycles, the voltage drop is across RL and which is equal to the input voltage. Okay. Now we will see some interesting ripple factors like the half wave rectifier. So basically, if you notice, there is no such extra things change because the basic definition is the ratio of RMS value of AC component to the DC component in the output. So basically what we find in the ripple factor, so we want to see that although we are saying that we have converted the AC into DC, but it is very much possible that there are still some AC components available in the output. That means we need to find it quantitatively, that how much AC component still available in the output DC component, and that ratio gives us this factor which is called the ripple factor. Okay, so the definition or mathematical expression, we can say that this ripple factor tau is equal to RMS value of AC component divided by DC value of the component. Okay, so this is the definition, and as we have noticed earlier also, this is the value. So that final value of tau is root under Vrms by Vdc whole square minus 1, and we will try to find the value of VRMS and VDC now, so that we can give the uh, corresponding value in this equation, and finally we will derive into a particular value. Okay, let's see what is the value for DC. Okay, here as you can see that VDC, how we will see that VDC? So it will be 1 over pi and the integration of the input signal Dm sine omega t d omega t, and the integration will be from 0 to pi obviously. So finally we see that it becomes twice Vm by pi. Okay, right? So after the integration we will see the value is twice Vm by pi. Okay, whereas once we find the VDC, we can easily see IDC as well, because IDC will be equal to VDC divided by RL, load resistor. Okay, so if we put the value of VDC here, twice Vm by pi, and the RL value is RL, so finally it becomes twice Im by pi. Okay, because Im is equal to Vm by RL, right? So what we can see here is that IDC is equal to twice Im by pi, and IRMS is equal to Im divided by root 2, right? So what we can see here is that the value of VDC is twice Im by pi, and the value of RMS is equal to Im by root 2. So these two values we need to remember. Next we will see some other value, or the VRMS value. So similarly, we will find the value of VRMS here also, and after the integration, we will see this is becoming Vm by root 2. So VRMS is equal to Vm by root 2. And now we will put this value of VRMS and VDC into this equation, where in the earlier slide we noticed that it was VRMS by VDC whole square minus 1, and we will put the value of VRMS, which is Vm by root 2, and VDC, which is twice Vm by pi. And as you can see, Vm will be cancelled out. That means this term will become entirely independent of Vm. So it does not matter how much is your V peak or V maximum. It will purely become 0.482. Okay. And if we go for the percentage, we can see that it is 48.2%. So finally we can conclude here that the amount of AC present in the output is 48.2% of the DC voltage. Okay, so you can clearly remember, or you can clearly notice the difference, as that for the half wave rectifier it was 121% more than the DC value itself. But as soon as we make it full wave rectifier, it has reduced to a certain number which is below 50% as well. Okay, so that means we have achieved something to reduce the ripple factor. Okay, now we will see some other parameters. Okay, so it comes first the efficiency. Okay, efficiency, as you know, efficiency will be basically the output power available divided by the input power which is supplied. Obviously, the efficiency in other words also, or intuitively you can understand that efficiency will be the output divided by input, that how much input is supplied and how much output you are getting, that gives you the efficiency of the circuit. Okay, so here for the case of ratio, we can easily see efficiency is denoted by eta, and this will be the DC power output divided by AC input power. Okay, and this one is denoted by PDC, and this is denoted by PAC. How we will get PDC? So PDC is equal to VDC multiplied by IDC, right? whereas your PAC will be is equal to VRMS multiplied by IRMS. Okay, so these two equations we will follow, and we already know the value of VDC, IDC as well as VRMS, IRMS. We'll simply just put the values of these things. Okay, so we can further simplify this without putting this formula as well. So both way you can do. So anyway, after putting all these values, we can easily see that this term will also be independent of Vm. So after putting the final value, we will see this is 8 by pi square, which is purely a numerical value, and essentially it becomes 81.2%. Right. That means the efficiency is 81.2%. So you can see that efficiency has doubled, because earlier for the half wave rectification it was 40, earlier it was 40.6%, and now it become, which is the multiplication of 2, which is become 81.2%, right? So this was for the half wave rectification. Half wave, this is for the full wave rectification, right? So full wave rectification just double the efficiency. So this is all about the efficiency thing. Now we will come to see the peak inverse voltage, right? So the maximum reverse voltage that a diode can withstand without destroying the junction. Okay, so what is the maximum reverse voltage it can withstand before being burned out? Okay, so for the full wave rectifier, this PIV is twice Vm. Okay, so the entire secondary voltage appears across the non-conducting diode. So the entire, please remember this thing, the entire secondary voltage appears across the non-conducting diode. Right. This is one important point to understand, which may be the disadvantage of this center tap based full wave rectifier. We will see this thing later. Right. Now we'll see some other parameters, okay, which is called the transformer utilization factor, TUF in short form, right? So what is transformer utilization factor? The average TUF in full wave rectifying circuit is determined by considering the primary and secondary windings separately, and it gives a full value of 0.693, full value of 0.693, right? So in this case we will see two factors. One is form factor. What is form factor? So it is basically the ratio of RMS value of the output voltage and the average value of the output voltage. This is called the form factor. So both are output voltage, but the one is RMS value and another is average value. And as you know, both are not similar. So obviously we will see that the RMS value of the output voltage is Vm by root pi, whereas the average value of the output voltage is twice Vm by pi, and finally we will see pi by twice root 2, which becomes 1.11. So the form factor is 11 for this case. Whereas we will see the peak factor also. So the peak factor is basically the ratio of peak value of the output voltage and the RMS value of the output voltage. Here is also both the factors are output voltage, but one is peak value and another is RMS value. So while we are putting this thing, we can see that the RMS value is Vm by root 2, as you noticed earlier also, and the peak value is Vm. It is already mentioned. So the peak factor is root 2 only, right? So this is, the value is root 2 only. And as you can see, both of these are not dependent on Vm at all. All these are numerical values only, not depending any of the parameters, right? So what we learned here is that for the case of full wave rectifier, the efficiency is just the double of the half wave rectifier, whereas for the half wave rectifier we'll see that the efficiency is half of the full wave rectifier. So it is easily understandable that the efficiency will be just be doubled for the full wave rectifier because both the halves are being rectified in the case of full wave rectifier. Okay. Another thing is ripple factor. While the ripple factor of the half wave rectifier was 121%, but for the case of full wave rectifier, it becomes 48.2%. So you can easily see that it has been reduced more than half of the half wave rectifier values. Okay, so this is also another advantage, right? And for the PIV value, I just told you before this slide to remember this thing. This might be an disadvantage of your full wave rectifier. Okay, we'll see these things now. Okay, now we'll see the disadvantages of full wave rectifier. So the first one is saying that the center tap transformer is bulky. Obviously, the center tap transformer has all these coils and everything, which makes it bulky. Okay, because this the total entire condition is bulky in nature and heavy also. So this is considered one of the disadvantage, not in terms of circuitry, in terms of bulkiness because of the bigger size and also heavier than the other components. Okay, so if we somehow can avoid these things, that will be much more better as compared to this center tap transformer, which is a bulky one. Okay, so this is one of the disadvantage of center tap based full wave rectifier, right? And the next one is it is difficult to locate the center tap on the secondary windings of the transformer. Okay, let's try to understand why this is difficult. Okay, so let's redraw this thing. Okay, this is the primary coil, right? Now we are considering the secondary coil, but sometimes it is very difficult that whether this point is center tap or this point is center tap or this point is center tap. It is really hard to understand that which point is the center tap. Okay, okay, let's give a different color. So you may think that okay, this could be the center tap, or you might think that this could be the center tap, but this keeps us guessing that which is the exact center tap because of the counting issue. Okay, the coil number of turns we need to count, and at the exact middle it will give the exact half voltage of the two ends. Okay, if it is like plus 9 and minus 9, total is 18 voltage, then you have to exactly find the middle. Okay, otherwise it will not be functioning as the center tap. Your voltage will be shifted, although it will rectify. It is not like that it will not rectify, it will rectify, but the voltage, output voltage, may not be the similar as we expect from our figures, right? Okay, now we will see the other effect. Okay, so the third one, or the third major disadvantage of the center tap full wave rectifier is that the diode must have high value, the diode must have high peak inverse voltage. Okay, so as you know, the peak inverse voltage of this type of uh, center tap based full wave rectifier is not that high, and the diode D2 or diode D1 for the case of different cycles has to withstand this much of peak inverse voltage sometimes, which is not bearable for the diode. That makes the circuit in risk of being burnt out. So to avoid these risks, we will be seeing our next video that to avoid these risks, we are going to introduce a bridge type of rectifier circuit which will avoid this discrepancy or the disadvantages of the center tap based rectifier, and we will see the efficiency and the ripple factors will be similar, but the peak inverse value will be better, and also we can avoid the bulkiness of the transformer, and also we can avoid the finding the center place of the secondary windings of the transformer. So all these things we will see in our next video, which will be the uh, bridge type of rectifier, full wave rectifier circuit. Till then, you can check our next video. Okay, see you in the next video, which will be the bridge type of full wave rectification. Thank you all.